Let us now discuss about the calculation of rate law or the order of the reaction, taking the simple and complex reactions. Now, see, the first case is the mechanisms in which rate determining step is given. I mean, the slow step of the reaction is given. Okay. Now, even in this also, we have two types. The first one is, see, the rate determining step involves only the reactant as well as product. Or the catalyst may also be present sometimes on the reactant side. Remember here, the rate determining step is given. In this kind of a case where the rate determining step involves only the reactant and product, it's a simple reaction. In such a case, you can straight away take the rate law of whatever the rate determining step is as the rate law of the reaction. Simply speaking, as of course we discussed earlier also, if the rate determining step has the reactants, has all the reactants, straight away you can write the rate law, of course from that the order, just considering the rate law of the rate determining step. So let me give you an example. Let us take this one, 2NO2 plus F2 gives rise to 2NO2F. For this, we are going to calculate the rate law, of course, from that the order of the reaction. Now, the mechanism of this is, of course, this is a question. The mechanism, of course, can be given as NO2 plus F2. See this, you got both the reactants. Rate constant here is K1. Here you get NO2F plus F. This, of course, is a slow step. Now, coming to the second step, wherein you are getting NO2F from the NO2 and F. Of course, this is the first step. Now, look at this. The slow step itself has both the reactants. So, no need to go for any other step or any other reaction. Straight away, taking the RDS into consideration, rate law or rate expression can be straight away written as K1 into NO2 into F2. Simple. But look at this. Here you got the stoichiometric coefficient as 2, but here you got just 1 as the power because you have considered the slow step in which the coefficients are 1 and 1. So the overall order of this reaction is 2, isn't it? Order is 2. And if you consider molecularity in these two cases, I told you very clearly that the molecularity is given for every elementary step of the reaction, not for the total reaction, right? If you consider molecularity of this one, what is the molecularity of this? Of course, you got two things reacting. So molecularity is 2. See, even for this also, because you got two things, even for the second step also, the molecularity is 2. I think now this is very clear. So here, remember, you will have the reactants and even the product, if at all the catalyst is also involved on the reactant side, even that will be there in the slow step itself. You can find everything in the rate determining step. So that makes it simple. You got NO2, you got F2, you got NO2F. Everything is there in the rate determining step itself. But every time it may not be the same. Let's see. Now, the second case in this. If the rate determining step has intermediate rate determining step has intermediate on reactants side. Okay. Now for this, see here, this of course makes it very interesting. It's a kind of complex reaction. Concentration of the intermediate has to be given in terms of concentrations of reactants and products. Or even the catalyst also. Taking equilibrium step into consideration. Now, this makes it very interesting. You will have an intermediate. So, the order, the rate law can be known only after writing the concentration of intermediate in terms of the reactants and products. But remember, in simple terms, what I can say is the rate determining step may not have all the reactants. So that is how we can identify. Let me say, let us take this example. 2O3 gives rise to 3O2. This is the decomposition of ozone. Now, coming to the mechanism of this, of course, we discussed. Look at this. Say this step is a fast step. In fact, it is an equilibrium step. This is going to play an important role. Now, this is the intermediate. Now, this intermediate will now react with another molecule of ozone. Let the rate constant be K3 to form O2. See, of course, the second step is the slow step. But the point is, in the slow step, you got just one molecule, but there is one molecule of ozone even in the fast step also. Okay. In the previous case, we had the reactants, all the reactants, products, and even the catalyst in the slow step. But here, of course, we got one molecule of that, but still we got one molecule of that in the first equilibrium step also. So in this case, we need to consider the first equilibrium step, from which we will of course be calculating the concentration of the intermediate. Let me give you. Let us now take the rate determining step. So according to the rate determining step, simply it can be written as the rate is equal to K3 into O into O3, right? From this step, the slow step of the reaction, I've written the rate expression, obviously, has to be. But the point is, you got something which is unwanted, this, right? One more thing is, you got another molecule of the reactant even in the fast step, right? Now, in this case, in order to get the concentration of the intermediate, yes, the intermediate here is oxygen, right? For that, you need to go to the fast equilibrium step. So, according to equilibrium step, can it be written as, say, K equilibrium is equal to K1, I mean the rate constant of the forward reaction by the rate constant of the backward reaction. So that can be given as O2, Simple, products by reactants. Concentration of the products by the concentration of reactants. That is, of course, the expression for equilibrium constant, right? Now, this is what we are going to. Okay, from this, we can get the expression for the concentration of oxygen. And that, of course, will be substituted in this expression. We'll see that. Now, the concentration of oxygen can be given as, it is going to be K1 into O3, right? By K2 into O2, right? So this is the concentration of O2. Now substituting this in the rate law, that is, rate is equal to K3 into O3 into O, what we have written from the slow step. Okay, so now rate can be written as K3 into, keep O3 as it is. Then what is O? K1 into O3 by K2 into O2. We have just substituted this here. Okay, now the final expression can be written as rate is equal to K1 into K3 by K2 into O3 square by O2. So if suppose this O2 is taken into numerator, it will become O2 to the power minus 1, right? See, from this is the final rate expression. I have an interesting point here. So order with respect to O3 is, of course, 2, whereas order with respect to O2 is minus 1. Special. I told you that the order can be negative, but with respect to a reactant, we don't have any reaction for which the overall order is negative, but we have reactions in which the order with respect to one of the reactants is negative. This is one such reaction. Okay. Now let us go for the second variety, wherein we'll be taking mechanisms in which rate determining step is not mentioned. Okay. So in this case, we will be going for steady state approximation, which is going to be very interesting. Now, in general, if we consider a reaction, See, initially, I mean, at the beginning, we will have the reactants only in the reaction mixture. Okay. But see, these reactants go on reacting to form an intermediate, which of course decompose, giving the products. Right. This is a basic reaction. If suppose we consider at the beginning or initially the rate of production or the formation of intermediate is more, or you can say it is large. Rate of production of the intermediate is large in comparison to the rate of its consumption. So simply right at the beginning, I mean, as the reaction is just started and it is going on, no doubt the formation of or the production of the intermediate will be large in comparison to this. I mean, the rate of its consumption or rate of its reaction into giving rise to products or rate of its decomposing into products, right? Now, but as the reaction proceeds, I mean, after some time, rate of consumption of the intermediate becomes equal to rate of its production. This, of course, is called steady state. Yes. Where the rate of consumption is equal to rate of its production. These two will now be the same. So this is what we call steady state. Now, as the reaction goes on, even after a steady state, I mean, when the reaction is going to get completed, what happens? Now, when the reaction is going to get completed, obviously the rate of consumption will be more than the rate of production. Its consumption or its decomposition into products will be more than the rate of its formation from the reactant. It's all a known thing. But the interesting part is most of the time, the reaction will be at steady state. Because most of the times the rate law will be at steady state, the rate law during steady state itself is taken as equal to the net or the final rate law of the reaction. Because see, the most of the times reaction will be at steady state. I can just give you the same thing in graphical way. Taking the concentration of the intermediate or rate of the formation of the intermediate versus time, whatever with related to intermediate, it can be given as this. Okay. See, this is how the rate of its formation slowly increases as time goes on. And then, of course, a steady state is obtained. And then, this is how it goes on decreasing. Okay. But see, most of the times it is at steady state. So the rate law or even the order of the reaction are given from the rate law of this steady state. So in general, at a steady state, see at steady state, deconcentration of intermediate by dt can be given as a 0. Remains the same because rate of its consumption is equal to rate of its formation. Okay.